We will wait for more 5 minutes, then we'll start. So can we start now?
Yes, sir.
Okay. My screen is visible, right?
Yes, sir.
Okay. Okay, good afternoon everyone. So today we will solve the assignment questions, practice question for the week 6 content, and the week 6 content includes the lecture 1, which include turning, planning, shaping, lecture 2, which includes milling and drilling, and lecture 3, which include grinding of metals and mechanics of grinding process. So have you solved the previous year assignment, previous week assignment, assignment 5?
Yes, sir.
So like it was easy, or you got any doubt?
No, sir, it was easy.
Okay, fine, na? Okay.
Yes,
So
sir.
okay, then we will go through the week 6 content first, which sir has already taught, and then we'll see some practice questions. Okay. Chalo. So first we will see the turning process. So do you know what does turning means, or what is turning process? Anyone? Hello.
Sir, it is used to reduce the diameter of a tool.
Yeah, right. So turning process is the It's a process in which a cutting tool removes the material from the outer diameter of a rotating workpiece. The main objective of the turning is to reduce the workpiece diameter. So basically we have a workpiece and we have a tool. Workpiece is rotating and tool is moving. Well, workpiece has a cutting motion and tool has a feeding motion, and the tool reduces the diameter of the workpiece. So this is a turning process. This is called the straight turning process. Basically we have different type of turning process: taper turning, helical turning, and straight turning. So generally we need to we will see here the straight turning process. The straight turning process is that process in which the tool is made to travel parallel to the axis of the rotation of the workpiece. For example, if this is the workpiece, if this is the workpiece, and this is the axis of rotation of the workpiece, then if this is a tool, for example this tool, then the tool move like this parallel to this axis of rotation. This is the axis of rotation, this is the workpiece, and this is the tool. So in straight turning, the tool movement of the tool, see, this is the cutting motion. It is rotating with an speed n rpm, and it is moving with an feed f or v something. So this movement of the work tool is parallel to the axis of the rotation of the workpiece. This is called straight turning process. Fine?
Yes, sir.
Okay. The cutting motion is provided by the workpiece. Since the workpiece is rotating, so therefore the cutting motion is provided by the workpiece, and the feed motion is provided by the tool. You can see here, this is the workpiece. This is the workpiece. One second. This is the workpiece, which is rotating within some speed, and this is a tool. This is a tool. Black one color is a tool, and this gray one is the workpiece. The tool is moving here like this. You can see. Tool is moving in this direction. This is with some velocity, or say with some feed Vf, and workpiece is rotating with some spindle RPM n. So this is the cutting motion is provided by the workpiece. See, so the cutting motion is given by the workpiece, and the feed is given by the tool. So here the cutting is the main motion, right, and the feed is the secondary motion. So the main motion is called genetrix. We have seen in the first class, genetrix, and the feed motion or the secondary motion is called directrix. So can anyone tell me what is the shape of the genetrix here?
Circular.
Right, because cutting motion is rotating, so genetrix will be circle. And feed motion?
Sir, straight line.
Straight line, right. Like this. Fine. So this is okay. Now we will see we'll see a video how a turning process is done. So please watch this video.
In straight turning, the tool is fed parallel to the axis of the work to reduce its diameter so that the final diameter is the same at each end. Removing a significant amount of material in one pass is called rough turning. The final lighter cut that creates a smooth surface finish is called finish turning. Taper turning produces a taper along the axis of the workpiece. Tapers are produced by offsetting the tailstock from center line or by using a taper attachment. Short, steep tapers can be turned using a compound rest. Contour turning or profiling was formerly performed by having the single-point cutting tool trace a template of the desired profile shape. This has largely been replaced by CNC turning, in which the desired contour is simply programmed into the machine, which directs a cutting tool to cut the contour. Forming is another alternative for generating complicated shapes. The tool having the desired form or geometry is advanced perpendicular to the axis of rotation, reproducing the tool shape in the workpiece. Forming is commonly performed on automatic screw machines. Chamfering eliminates sharp corners from a workpiece and is a good safety measure. Typically, chamfering breaks corners at a 45-degree angle. Grooving creates a groove or recess using a tool that is usually the size and shape of the required groove. Some grooving tools can also widen a groove by traversing side to side after plunging into the workpiece.
Okay, so you have seen different turning processes. Straight turning, in which the simple straight workpiece is produced. Taper turning, where a taper workpiece is produced. A counter turning, where complex shape workpiece is produced. Other similar kind of process include the grooving and all, and chamfering and all. So you have seen that. So basically this is the way how the turning is done, right? Now we'll see some of the turning process parameters. If you are turning a workpiece with the help of a cutting tool, then you require some process parameter so that what is the speed of the workpiece, what is the feed of the tool. So what should be the depth of cut, what should be the speed. This everything comes under the process parameter of turning. So we'll see one by one what are the various process parameters involved in turning. First, cutting speed. Cutting speed is the speed of the workpiece by which it rotates. है ना? So how we calculate the cutting speed? Cutting speed is calculated by pi dn, where d is the dia of the workpiece, where this d is the diameter of workpiece, and this n is the spindle rpm, the speed at which the workpiece rotate. So using this p is equal to pi dn, we calculate the cutting speed. Okay. Second is where d is the diameter of the workpiece and n is the spindle speed. We have already discussed. Second is the feed velocity. Feed velocity is that velocity by which the tool moves along the workpiece so that it can cut the workpiece, right? That is called the feed velocity. So what is the formula of feed velocity? Small v is equal to f by n, where f is the feed rate. It is the feed rate, it is the feed at which the tool is progressing, and n is the spindle speed. So feed rate is given by in mm per revolution. Mn in revolution, why? Because see, workpiece is rotating, workpiece is rotating and tool is moving. Tool is moving like this. It is n, it is f. So in one rotation of workpiece, how much distance the tool moves, this is called the feed rate. For example, in one complete revolution, if feed moves something distance, that is the feed rate. So that multiplied by n is called the feed velocity. So second, we got the feed velocity. Third is the undeformed chip thickness. Undeformed chip thickness is that thickness of the workpiece which is not been deformed or which is not been cut. Right, we have seen in the single point cutting process, we have seen this is the workpiece, this is the workpiece, this is the tool, and this is chips are formed, these are chips are formed, right? So this is the chip thickness, this is the chip thickness, but this is still not cut, this is still not cut. This is called T, this is called the undeformed chip thickness. So in turning also, the workpiece which is still not cut is the undeformed chip thickness. Okay, and here the undeformed chip thickness is given by f cos gamma s. Please note f cos gamma s. What is gamma s? Can anyone tell me what is gamma s? Hello? Hello?
Shear strain, sir.
What?
Shear strain.
No. See, it is cos, So with cos, how can shear strain come? With cos, some angle should come, Can you tell now what is gamma s? Gamma s is side cutting edge angle. Side cutting edge angle. We have studied this na in the tool geometry. If this is the tool, for example, if this is the tool and this is the main cutting edge, right? And this is the y-axis. Then this angle gamma is gamma s. This angle is gamma s. This is the gamma s. Acha, if in question you don't have gamma s, you have gamma p, then what you will do? Can anyone tell me?
90 minus gamma p.
Right. So gamma p plus gamma s is 90 degree, because this is gamma p. This is gamma p. So gamma p plus gamma is 90. So in question, if you have gamma p, then use 90 minus gamma s to find the gamma s. Right. So the formula for undeformed chip thickness is F cos gamma s. Now where gamma is the side cutting edge angle. One is the undeformed chip width. So one is the, see, chip is like this na. Chip is like this. It is a 3D object. So it has some, it is like this. So this is the thickness, and this is the width of the chip. This is the width, B. So the value of B is given by D by cos gamma s. Right? So where D is the depth of cut, what is the depth of cut of the tool, and gamma is the side cutting edge angle. Okay. So this is okay. Everyone got this?
Yes, sir.
Okay. So this formula you need to remember. What is the formula of undeformed chip thickness? What is the formula of undeformed chip width? And gamma s, if gamma p is written, then how to convert to gamma s? This we have already discussed before also, and now also you need to take care while solving the numericals. Okay. Next. So what we will see the various forces and power in turning. So in turning, we'll see different forces which are acting in turning, and like which forces are responsible for the consumption of powers. Right? See, mainly there are three components of forces. One is Fp, which is the cutting force in the direction of the cutting velocity. One is Fq, which is the feed force in the direction of the feed motion, and Fr, the thrust force which is perpendicular to the surface. See, this is turning tool, right? This is turning, this is workpiece, this is tool. See, one force will be along the direction of the cutting velocity, right? One force will be in direction of the cutting velocity. Wait. Take. See, if this force Fq is in the direction of the cutting velocity, right? If cutting velocity is in this direction, then Fq will be in this direction, right? See, if tool is moving like this, then one force is in the direction of the 1 second. Wait. This sorry. This is not. See, this is workpiece. Workpiece is rotating like this, na? So if this is workpiece and it is rotating like this, then cutting velocity will be here like this. This is cutting velocity V. So in this direction there would be a force which is called Fp, which is called the cutting force in the direction of the cutting velocity. Now see, tool is moving like this, feed. Tool is moving like this in the feed direction. So along the feed direction there is the force called Fq. See, Fq, which is the feed force in the direction of the feed motion. And now one force is that which is radially perpendicular to the surface. This is the surface. This is the workpiece surface, and one force is perpendicular on the radial direction to the surface, which is called the radial force or the thrust force. These are the three main forces which are being there in a turning process. So if you want to calculate the resultant, simply we know the resultant force is under root f square p plus f square q plus fr square. This you can find if you know the three forces. Now, to calculate the power, so the power is consumed mainly by the cutting force, because the cutting force is mainly responsible for the cutting of the workpiece, right? So mainly the friction will develop during the cutting only. Majority of the heat will generate during the cutting only. So majority of the power consumption is because of the cutting force, right? So therefore we will calculate power based on the cutting force. So the power is given by Fp into V bar. So what is V bar now? See, Fp is the cutting force. but V bar is the mean cutting speed. So you'll say ki why mean cutting speed? Why not the cutting speed? Because see, in turning process you have a dia something D2, and you are have two dias, right? D1, because you have reduced from one dia to another dia. So because of, then we will have two different cutting speeds, then one for D1 and one for D2. Therefore, to normalize that, we use a average dia. This is called D. This is called D, where D is what? D1 plus D2 by 2. Right, D1 plus D2 by 2. So this mean dia have a speed called V bar, which is called the mean speed. So using that mean speed, we calculate the power. Have you got this?
Yes.
Hello? Hello?
Yes, sir.
Anyone having any doubt?
No, sir.
Fine, na? You got na how we calculated this mean dia? Why we calculate this mean dia?
Yes, sir.
Okay, we calculated this mean dia because in turning we have two diameter, because you're reducing a diameter, na? Then you will have two velocity, but we need a single velocity. Therefore, we calculated a single diameter, which is called the average diameter. From that, the velocity corresponding to that average diameter is called the mean diameter. And using that mean diameter, we calculate the power using the cutting force. Okay. Now specific cutting. Now two new terms I am going to introduce. One is the specific cutting energy and one is the MRR in turning. So specific cutting energy. What is specific cutting energy? Anyone knows? Anyone know what is specific cutting energy?
No, sir.
Okay. See, when you are turning, right? When you are turning, you are doing any machining. Then what is your aim? Your aim is to remove the material, right? You want the maximum material to be removed. Therefore, the specific cutting energy is that energy is that power which is required to remove a material from the cutting, from the workpiece. So it is defined as the energy required to remove a unit volume of material, right? So specific cutting energy is given by power upon Zm, where Pw we have already seen the power, and Zm is the material removal rate. So how much power is required to remove a unit volume of material? It is called specific cutting energy. So this power we have already seen is the power consumed, and Zm is the material removal rate. So material removal rate is the how much volume of material is removed per in a time, per minute or per second, anything. So material removal rate, and how it is calculated, it is a product of the mean cutting speed and the chip cross section area, right? The material removal rate is the volume of the material removed per unit time, and how it is calculated, it is a product of the mean cutting speed and the chip cross section area. So what is Zm? So mean cutting speed is what? V bar. We have seen the mean cutting speed V bar. So V bar into AC. So V bar we can write pi dn. So pi d bar into n, and AC can be written as F into D, where F is the feed and D is the depth of cut. Okay. So this way you can calculate the material removal rate. Have you got this?
Yes, sir.
Please, if any doubt, please ask. I'll explain again. Okay, then we'll move to next slide. Now surface finish. See, when you are doing any machining, your one aim is what? To increase the MRR. See, if you're doing any machining, your aim one is that to increase the MRR so that you can get higher output. Second aim is to have good surface finish, because if you'll have good MRR but the surface of your workpiece is not that good, it is not having good dimensional tolerance, good accuracy, good the dimensionality of the workpiece is very good, the surface is very smooth, it has no roughness, it has no other different irregularities, then your purpose of machining is fulfilled. So therefore we need a good surface finish. Now we will see what are the irregularities which are happening in the surface and how to calculate that. See, the surface finish in a machining operation, it mainly depends upon first the type of chip formation, tool profile and geometry, and cutting condition. So basics of what type of, for example, in brittle material we have seen the discontinuous chips are formed. For ductile materials, the continuous chips are formed. So based on the type of chip formation, we can say what is the surface finish. Tool profile, like depend upon the type of tool also we can say if the rake angle is highly negative, we can say the tool is very strong and chips have difficulty to flow. If the rake angle is highly positive, we can say the rake angle then the tool is very soft, the chip has very easy to flow. So and the cutting condition, like high speed, high depth of cut, high feed, what is the in this condition, what is the surface of the workpiece. So this condition determine whether the surface of the workpiece is good or not. Now we'll see. Up now, when we talk about surface finish or surface roughness, it is talked in terms of few terms. Okay, so basically when we talk about the irregularities, for example, see, we have a surface, right? We have a surface. This is a very smooth surface. See, very smooth, no irregularities, flat surface. But in general, it is not like this. It is like this. The surface is like this. This is like this. This is like this. So here the surface is not smooth. It has some irregularities, right? It has some irregularities. So this is irregularities correspond to the surface roughness. Surface roughness. So now we will see how these irregularities, what are different type of irregularities which correspond to the surface roughness. First is the peak to valley height. Okay, what is the peak to valley height? It is a root to crest value of surface roughness. Now what is this? We'll explain this. See, this is the workpiece, this is the center line, this is the very higher position of the irregularities, this is the lower position of the irregularities. This higher position is called peak, right? And this lower is called the valley, or this higher is also called the crest. It is called the root. The distance between this peak and valley is called peak to valley height, which is called h. This distance, for example, this is the workpiece and this is the irregularities. So distance between this valley to this peak, this distance is called this peak to valley height. Okay, this is number one. Number two is the center line average. So you have different peaks, different valley, but you need to find the average of that peaks and valley. So this average is called the center line. This you have denoted doing the average, and this average is called the center line average. So how it is found, the center line average? It is found by doing the averaging of the height of the surface above and below the center line or a sample length. Okay, if this is a sample length, then you will do the average of y1, y2, and every average of above and below, and the resultant value is called the center line average. Fine. So how to find the center line average? I'll show you. 1 second. See, if you want to find the center line average, just you take the value and don't take the negative value. Don't take the below value to be negative. For example, if some value is 1, here 2, and here is -3, then just find center line average to be 1 plus 2 plus 3 and total value by 3. So its value is 2. Okay, you always should take the mod or the positive values, right? Just sum it, take the average, and then find the value of the center line average value. Okay, one is the 1 second, someone is joining. 1 second. Okay. Now one is the RMS, root mean square value. It is the square root of the mean of the square of the ordinate of the surface from the center line. See, it is just another representation to find the surface finish. This RMS value you find just the like way you find the mean and standard deviation. Na? Similar way you find the root mean square. Just to get the more accurate and more precise value, we find the root mean square value. So in this, what you do, just square every value, divide by the number of values and do the square root. Fine. These are the three values. One is the h, which is the distance from the peak to valley. One is the center line average, which is the mean of every value, keeping every value to be positive. And third is the root mean. You square it, add it, divided by the number of observation upon the square root. Okay, this is fine.
Yes, sir.
Okay, I'll move forward then. Now, this peak to valley height, when you are calculating peak to valley height, so see what happened. It has ways to calculate. For example, wait. If your cutting tool is very sharp, see this cutting tool is very sharp, है ना? Cutting tool is very sharp. You can see. This is the workpiece, right? Now it is moving in this direction. It is feed in this direction. It is now here. Second movement, it is here. Third movement, it is here. Okay, it is coming from here to here to here. When you see this, you see this portion is not cut, right? This portion is not cut. It is very less, but it is not cut. So this corresponds to the surface roughness. This is the height h. This is the height which corresponds to the surface roughness. Similarly, if your tool is not sharp, it is for the sharp tool, which is very sharp. And if your tool is having some cutting edge radius, then your tool is like this, somewhat like this, some radius. So it will move now like this. It is moving like this. So this is the portion which is not cut. See, this is the portion I'm coloring it. This is the portion which is not cut actually. So this portion corresponds to the surface roughness. So this is the height. This height is the surface roughness. So this we need to calculate. Okay. So I'm not deriving it. I'm just, if you'll say I'll derive it also, but I'm just writing the formula. For sharp edges, its value come out to be f upon 10 gamma s plus cot gamma e, where gamma is the side cutting edge angle and gamma is the end cutting edge angle. Right. This is the formula for the surface roughness for a sharp tool. Right. Now, when we consider the tool with a cutting edge radius, then if cutting edge radius, then we'll have the radius also, right, for the tool. In that formula, in that case, the surface roughness value is f square by 8r, where f is the feed, r is the radius of the nose radius of the tool. This is fine.
Yes, sir.
Okay. If you want a derivation also, then you can ask. We can derive it. Okay. If you want to try, you try. If you cannot, then we will derive in the next class. But for now, you remember this formula. These are the very important formula. These are the very important formula. Both formula very important. F upon 10 gamma s plus 10 cot gamma e, and for this nose radius h equal to f square by 8r. If you will give gate exam, if you'll give, then this formulas are very important. They ask like lots of questions from these formulas. Okay, so should I move to the next slide?
Yes, sir.
Okay. So when you see the graph between the surface roughness and the parameter, I'll show you. See. See, we'll see surface roughness increases very highly with the feed. You can see directly here only na कि surface roughness is directly proportional to f square. So if f will be 1, then h will be 1. But if it increase f to be 2, h will become 4. Right from here. So with feed it increases very drastically like this. So when we increase the feed rate, surface roughness also increases. Therefore we cannot the feed rate directly without like increase it. We have to keep an optimum feed rate. See, if we increase the feed rate, obviously your MRR will increase, but we cannot, if your MRR increases, doesn't mean our surface finish also surface finish also decrease, right? The surface roughness increases. So because of that, we should use the optimum value of feed rate so that we can get both a good surface finish also and a good material removal rate also. Okay. Next we can see when we see the graph between surface roughness and cutting speed, we see कि surface roughness increases for a cutting speed for a particular cutting speed, then it start decreasing. 1 second. Can anyone tell me why this is happening? First it is increasing, then it start decreasing. Can anyone tell me? Anyone have any idea? See, at starting when the cutting speed is increasing, it has a very small cutting speed. So at that time, because of that high cutting speed, because of that force is increasing, like you have a force dominant region. Because of that surface roughness is increasing because depth of cut is increasing, feed is increasing. But when the cutting speed is becoming more and more high, what happens? We have seen in last class, if cutting speed is more high, then temperature increases, right? When temperature increases, then the workpiece becomes softer, and the workpiece becomes softer, then the machining would be easy. Machining become easy. Because of that, the surface roughness decreases. We'll have a smoother surface. Understood? When the speed is very high, then the temperature increases. Because of the temperature, the workpiece becomes softer, and because the workpiece becomes softer, the machining will be very easy and surface roughness would decrease. This is the reason why with increase in cutting speed, later on the surface roughness decreases. Have you understood this?
Yes, sir.
Okay. Then we will move forward. Now our turning part is over. If anyone having any doubt in turning, please ask me. Then we'll move to shaping and planning. Hello?
No doubt, sir.
No doubt? Okay. Now we'll move shaping and planning. See, shaping and planning is nothing. It's just Acha, can you tell me, I have taught in the first class, for shaping, what is the genetrix and directrix? Can anyone tell me? I have told this in the first class. Anyone remembers? Hello? No? See, in both shaping and planning, we have a linear motion. Then the genetrix and directrix both would be a straight line. Straight line, here also straight line. Right? Shaping and planning both are similar process only. Difference is that in one the cutting motion is provided by the workpiece and the feed by tool, and in other the cutting by the tool and the feed by the workpiece. So see what happened in shaping, the cutting speed is provided to the tool, means the tool is giving the cutting speed and the feed is and the workpiece feed. But in the case of planning, there is opposite. feed is given to the tool, and the workpiece is provided by the cutting speed. So we can say that in case of shaping, the cutting speed is to the tool, then the tool motion is primary, which means that the cutting speed is the generatrix and the feed motion is secondary. So therefore the movement by the workpiece gives the directrix. But in the planning, the feed is given by the tool, the movement of tool gives the directrix, and the workpiece movement is given by the cutting speed. So the generatrix is given by the workpiece, just opposite, nothing else. We can see here in case of planning, see planning, tool is moving, giving a feed motion, see, and workpiece giving a V main motion. But in case of shaping, see, in case of shaping, the tool is given as cutting speed, but the workpiece is given a feed. This is just opposite, rest are same. Is it clear? Do you understood what is this?
Yes, sir.
Okay. Now this was very small. Now we will go to milling. Milling is very important part of the very important type of machining. So can anyone tell me what is milling? Any idea about milling?
Milling is the process of cutting material by the multiple point cutter.
Right. This is one of the very good point. Any other point? This is very good. So this what we have seen: turning, shaping, planning. This were the single point cutting tools. Means they were cutting the material from a single point. But milling is a multi-point cutting tool in which the cutting takes place by the multi-point of the tool, right? Multiple edges. You can have single, 2 edges, 3 edges, 4 edges, 6 edges, 8 edges even. So this is a multi-point cutting tool, milling. And if you'll see milling, see the material is removed by rotated cutting tool with a large number of cutting edges rotating about the fixed axis. So in milling, a rotary tool is there or a rotary cutter is there in which material is removed by a large amount of cutting edge. In there we have a single cutting edge in turning, in planning and shaping, but in milling we have a large amount of cutting edge which removes the material. Second is the axis of rotation of the cutting tool is perpendicular to the action of the feed. For example, see, this is the milling cutter, right? This is a milling cutter. This is a tool. It is a tool. It is a milling cutter. It has, for example, 2 edges. One edge this and one edge, 2 edge. It is having 2 edges. So the direction of the rotation of the edge is perpendicular to the direction of the feed. So this is the axis. Tool is going downwards, right? Tool is moving like this. This is feed, and this rotation is perpendicular to the feed. It is saying like this. Now, the milling operation requires a milling machine, a fixture, a workpiece, and a milling cutter. This is very obvious. It is one of the most versatile operation. Why milling is one of the most versatile operation? Because we have different types of milling operation and different type of milling cutters which can perform different type of operations. Like if you want to make a hole, or if you want just to make a slot or any complex geometry, then milling cutters are used, and milling operation is very useful. In milling, what happens? The feed motion is provided to the workpiece and the cutting speed of the cutter. है ना? So the cutter is rotating, right? The cutter is rotating, and the workpiece is given the feed motion, right? It is normal. It is, you can see it is one of the example of the face milling, where you can see this is the milling cutter. This is the milling cutter, this one, and this is the workpiece. You can see earlier this workpiece had this height, but we have reduced this height from this to this. You can see by milling on the face of the workpiece. Therefore, it is also called face milling. This particular milling, because we are milling in the face of the workpiece, right? So see, the cutting is action is provided to the, this is the cutter, and see how many edges. the orange color, you can see orange color. These are the cutting edges. So 1, 2, 3, 4, 5, 6. It can have up to 6, 8 cutting edges. Therefore, it is called multi-point cutting tool. So the cutting motion is pointed to the tool. See, the tool is rotating. This tool is rotating about this axis, and the cutting is pointed in the cutter like this, and the feed is pointed to the workpiece. See, workpiece is moving in this direction. So like this, the cutting is happening. Okay. Now we will see the classification of milling operation. So milling operation are mainly classified into two types. One is plane or horizontal milling, in which the cutter axis is horizontal. Okay. For example, now the cutter axis was vertical, right? But if the cutter axis is like this, horizontal, it is called plane or horizontal milling. Okay. This plane or horizontal milling includes two types of milling. One is up milling and one is down milling. So what is up milling and down milling? See, up milling is a type of milling in which the cutting and the feed direction are in opposite direction. For example, this is the workpiece, right? And this is the milling cutter. This is the milling cutter. Okay. For example, this workpiece is moving rotating like this, anti-clockwise, counterclockwise. So when you see this point, right, its direction is this. Sorry, it is clockwise, not clockwise, not counterclockwise. It is clockwise. So when you see here, this direction is this cutting speed, and the workpiece is moving here, feed. So you see the cutting speed and feed direction are opposite to each other. This is called up milling. But when it will rotate like this. For example, if it will rotate like this, anti-clockwise. So when you see here, its cutting speed is V here, and the feed direction is also here on the same direction. It is called down milling. So in case of up milling, the cutting and the feed motion are in opposite direction, but in the case of down milling, the cutting and the feed motion are in the same direction. This is a type of the horizontal milling. Okay. Second type is the vertical milling. Vertical milling, as we saw here, the axis is perpendicular. See, it is perpendicular to the workpiece. So in that type of milling is called the vertical milling. The cutter axis is perpendicular to the workpiece surface. So here we have different types of milling called slot milling, face milling, T-slot milling, depending upon the type of operation what we need. See what you have taught, what I have shown you, up and down milling. See up milling, it is moving in this direction, but the speed is in this direction. It is opposite. It is called up milling. But in down milling, you can see it is moving in this direction only, V, and the workpiece is also moving in this direction, both in the same direction. This is called the down milling. Have you understood what is up milling, down milling? Any doubts? Hello?
No doubt, sir.
Okay, fine. Then we'll see some of the differences between up and down milling. So these are very theoretical differences. In down milling, the net force is directed upwards, downwards, and its vertical component keep pressing the job against the table. In up milling, it starts from a zero thickness.
Sir.
Yes. Hello.
Sir,
Yes.
Sir, in up milling,
Yes.
the feed force will be more. It will be required more or what?
What you are saying?
Because the cutter speed,
Mm-hmm.
the direction of cutting, and the feed is opposite na. So in that case, the feed force, in the force given for feed motion will be high.
Okay. What you are asking or you are telling?
No, I am asking, sir.
Okay.
I-
See, you are talking about the feed force, right?
Yeah.
See, the phenomena is like this. In up milling, what happens? You are talking about the up milling, na?
Up milling. Money compared to down milling, up milling, the feed force will be high or what?
Actually, you can say like this. In up milling, na, what happens? your chip thickness, the removal start like this. You start from 0 and then you go upwards, right? 1 second.
Yeah.
So it start from the 0 to maximum in up milling. 0 to maximum, right? So there is a net pulling, one net upward force here. This is a workpiece. This is a net upward force. So this net upward force pulls the workpiece up in upward direction, right? It pulls the workpiece in the upward direction. Therefore it always tend to pull the workpiece. Because of that, we require a strong fixture here, right? So wait 1 second. Therefore, because of that, it what to say? It bite the material. I'll tell you exact. 1 second. 1 second. Achha, this comparison of feed force I'll tell you, because I think the exact comparison of feed force I need to see that. I'll just tell you in a while, okay? Hello?
Yes, sir.
Okay. See, actually what happened in actually the phenomena is like this. In up milling, the chip thickness varies like from 0 to maximum, like this. But in down milling, it varies from maximum to minimum. Okay, so we know that if feed increases, then chip thickness increases. Okay, so in case of up milling, the feed gradually increases. So if you want to know the comparison, so in up milling the feed gradually increases, and in down milling, since the chip thickness is decreasing, the feed is decreasing. Therefore, if feed is decreasing, so in down milling the feed force is gradually decreasing. This you wanted to ask, na?
Yeah.
So are you clear now?
Yes, sir. Yes.
Okay, fine. So these are some of the derivations or differences. Now we will go to the process parameters in milling. Like in turning, there are different process parameters in milling also. So one is the undeformed chip thickness. See, undeformed chip thickness is the most important process parameter in every machining process. So when we talk about the plane milling, when there is simple plane milling of plane surface, I am directly writing the formula because derivation has already been taught in the class. So the value of this undeformed chip thickness is given by this V n under root d by d, where d is the depth of cut, big D is the cutter diameter, small b is the chip width, v is the table speed or the feed velocity. This v is the table speed, is called feed velocity. N is the RPM of cutter, and small is the number of the cutter. Okay, see, this V is called table speed. This table speed is nothing but the feed velocity, which is given by this what to say, F into N, right? And N is the number of teeth of the cutter. If the cutter has 4 teeth, it will be 4. If it has 2 teeth, it will be 2. So this formula you need to learn. One more formula is there. If you ask what is the maximum undeformed chip thickness, that maximum is approximately equal to twice of T, which is the undeformed chip thickness. So undeformed chip thickness is V by N under root d by d, and its maximum value is 2T. It is the approximated value. It is not the actual value. It is the approximated value. You just need to remember this formula. It is very important. Okay. Can I move to the next slide? Can I move to the next slide? It
Just
okay?
1 minute, sir. Writing down.
What?
Noting down, sir.
Okay, please note down. Please let me after you note down. Let me know.
Okay, sir.
Okay. And in second is the phase milling. So in phase milling, the value of this T is given by V by Nm 1 minus half B by 2D whole square is just the formula where 2B is the width of the workpiece. So this also you note down. This is for the plane milling, this is for the phase milling. So if you need to remember both formulas. If you want to note down, please note down this also. Just a formula, you need to remember the formula. Please write every formulas separately on a piece of paper so that when you revise, you will see each and every formula together so that it would be very easy for you to revise. Okay, can I move to next slide?
Yes, sir.
Okay. Now, similarly, when we have seen the surface finish in milling, similarly we can see the surface finish we have seen in turning. So we will see the surface finish in milling. So in milling also, but the formula for the surface finish for in phase milling is different. It is V square upon 4D n square, where we know V is the feed and this D is the cutter diameter, N is the number of the cutting edges, and N is the spindle RPM. So this you need to know. This formula is very important. Like we have formula for the turning, na, that F upon 10 side cutting edge angle plus chord and cutting edge angle, and for nose radius F square by 8R. So this is the formula V square upon 4 D n square for the surface roughness in phase milling. You need to remember this very important formula. Very important. This you need to learn. Okay. Can I move to next slide?
Yes, sir.
Okay. Now, you have any doubt in milling? Then we'll move to drilling. See, this has been already taught in the class. That's why I am going a little faster. But still, if you have any doubt, you can ask me. We can stop and clear it. Okay. So now we'll move to drilling. So can anyone tell me what is drilling?
So removing the material.
Then removing material to is every machining process. Now what is drilling? Like someone told me कि in milling we have multiple cutting edges point, है ना? Last time. So in drilling, what is the difference? What is the difference between the drilling and milling?
Process of removing metal in symmetrical form.
See, basically the major difference is that in milling you have multiple cutting edge 2, 3, 4, 5, 6, but in drilling you have only 2 cutting edge. There are only 2 cutting edge. You can't have more than 2 cutting edge. This is a major difference. Here it is a hole making process in which the drilling cutter it moves and makes a hole. Basically it's a hole making process, but it has only 2 cutting edges. But in milling you can have multiple cutting edges, 2, 3, 4, 5, 6, right? It's commonly hole making process, and the tool is fed in the direction of parallel to the axis of the tool. So basically, see, these are the various thing. Basically, this is a tool. See, this is a tool, and this is a workpiece, and it is fed in the tool is rotating, right? Tool is rotating like this, and it is moving in this direction. So what is the genetrix here? Can anyone tell me? This is feed.
Circle, sir.
Right. So cutting action is the main action. So this is the genetrix. And feed is the secondary action. It is the directrix. Fine. So basically it has 2 regions. One is the cutting edge here. This is the cutting edge. And one is the, see, when you see the top view, when you see the top view, then this is the cutting edge. And this between there is something which is called chisel edge. So they are mainly responsible for the cutting action. This is the basics, nothing more to be noted. Now, see basically two, 3 things you should know about drilling. First is, see, if this is a drill, right? This is a drill, है this is a drill. This is the cutting. This is the drill. This is the axis. These are the cutting edges. Okay. So this angle is called the point angle. This angle is called the point angle, right? The angle between this cone and if you draw a tangent to a major cutting edge, for example, you'll draw a tangent, and this angle between this tangent and this center line is called the helix angle. This is called helix angle, right? And one more angle is there which is called the rake angle. So rake angle cannot be shown here, but rake angle definition is same only between the rake surface and the which I have learned. So drill also have a rake angle which cannot be shown in the 2D figure. So this helix angle and point angle are same. It remain constant. But what happened to rake angle? Rake angle varies. See, I'll give you a very, very good concept. You should remember this. If rake angle, how it varies? For example, from the center, this is the center of the drill, to the periphery. This is the periphery, the outer boundary is the periphery. See, center is the core, right? Center is the core. So at center you want drill to be very hard, very strong. Therefore at center the rake angle, if alpha, it is alpha is highly negative, because negative rake angle are stronger. The tool with negative rake angle are very stronger, right? But however, when you go to the periphery here, what happens? At periphery you want the chip to flow very easily. So when you want the chip to flow very easily, you need a rake angle to be highly positive. So at periphery the rake angle is highly positive. So what happened? How the rake angle varies in the drill? In the center it is highly negative to facilitate strength of the drill, but at the periphery it is highly positive to facilitate the good chip flow. So this negative is to strength, to improve the strength, and this positive is to improve the chip flow, right? This is the and at periphery, see here it is negative. When you are going from here to here, it keeps on increasing from negative to positive. But at extreme periphery, at the boundary, this rake angle become equal to the helix angle. See, this no one will teach you. If you want to note, please note it. This is very important. the rake angle is negative at the center. As we go towards the periphery, rate angle started becoming positive, and at the periphery, at the extreme end, the rake angle become equal to the helix angle. Please note it if you want to. This is very important. Are you noting? Can I move forward? Hello?
Yes, sir.
Yes, sir.
Can I rub it? Can I rub it now?
Yes, sir.
ठीक है तो बेसिकली this alpha, the rake angle, I have told you the rake angle varies when you are moving along from the center to the periphery along the radial distance. So this rake angle, which is called the normal rake angle, it is defined by a formula called this, where tan alpha n is equal to Ra tan psi upon d by 2 beta by 2, where beta and psi are the point and helix angle. Beta is the point angle and psi is the helix angle, and d is the diameter of the drill, and this Ra is the distance along which it is changing. When you are going from center to the periphery, so you are moving along a distance, that distance is called the Ra. Okay, so this formula you need to remember, very important. This normal rake angle is equal to tan of alpha n is equal to Ra tan psi upon d by 2 sin beta by 2, where psi is helix angle, beta is the point angle, d is the diameter of the drill, and Ra is the radial distance along which the rake angle is varying. Similarly, what happened if you want to find the value of rake angle at the middle of the cutting edge, not at middle of the drill. So see, we have two cutting edge. So this is for example, this is the tool, this is the drill, this is D, complete is D, but cutting edge, this is RA na, this is RA, this is RA. So at the middle of the cutting edge, so this half, so this will become D by 4 na. So at D by 4, what is the value? Just put the value of RA to be D by 4, then you can solve it. Nothing else. Just put RA is equal to D by 4, because total is D and RA is half, so half of RA will be D by 4. So when in question it will ask find the value of rake angle at the middle of the cutting edge, then it should be D by 4. It will ask what is at the middle of the diameter tool axis, then RA will become D by 2, right? Hello? Understood this? You have understood? Hello?
Please repeat once.
Okay, see. This is the formula of rake angle, right? I have explained that rake angle in the center is negative. As we move towards the boundary, it becomes positive. I have explained, right? So rake angle formula is Ra tan psi by d by 2 sin beta by 2. So this you can find. Sometime in question it asks find the value of rake angle at the center of the cutting edge. So see, total distance is d, total diameter, and we have two cutting edge. So one cutting edge is this one, and second is this 2. So this is how much? D by 2, and this is d by 2, d by 2, d by 2. So if it is asking at the center of the cutting edge, so this is the cutting edge, its center will be here, then this will be d by 4 na. So we will put Ra value d by 4 and solve. But if it will ask find the value of normal rake angle at the center of a drill, sorry. So this is how much? This is d by 2. So at center of cutting edge, RA will become d by 4, and center of drill, it will become RA is equal to d by 2. Just put in the formula and solve it. Okay now?
Okay.
Fine.
Yes, sir.
Now we will see the process parameter in drilling. So in drilling also we have the undeformed chest thickness whose direct value is given f by 2 sine beta by 2, and chip width whose value is d upon 2 sine beta by 2, where beta, you know, beta is the helix angle. Beta is a point angle, f is the feed, d is the drill diameter. So these two formula you need to need to remember. These are very important formulas. This is very important and this is very important. This you need to know. Okay, the undeformed chip thickness and the chip width. Okay, now talking about the forces in drilling. In drilling also we have, similar to turning and milling, we have three forces. One is along the tangential component, one is along the radial component, and one is along the thrust component. So this is the similar in case of here. See, this is the cutting edge of drill. So one is along the tangential component. This is FP is along the tangential component, which is called FP, and one is F dash Q, which is normal. See, this is the cutting edge. For example, if this is a drill, this is the cutting edge. One force is along this cutting edge, which is called FP, and one is perpendicular to this. It is called F dash Q. Take now in this F dash Q is divided into two forces. One is the radial component, which is along the radius of the drill, and one is the FR, which is the thrust component FQ. So this is the contribution of forces. If you want to find the total value of tangential forces, then this is the value. Total tangential forces is 2 times of Fp plus Fp1 plus Fp2, where Fp1 and Fp2 are the tangential component due to the friction and extrusion, which is generally neglected. So we write Fp total is twice of small fp, where small fp is the force on the tangential direction. So we have two cutting edge, so total force will be twice of fp, right? We have one along this cutting edge and one along this cutting edge, so total force will be twice of fp. Similarly, f dash q also will be twice of fq, which are almost same. So this is about the forces in the drilling. Have you understood? Hello? Any doubt? Hello? Are you there? Hello?
Yes, sir. Yes.
Have you understood, na?
Yes, sir.
Okay. Now we will quickly move to grinding. Can anyone tell me what is grinding? This is our last topic for the today. Then we'll move to the question answer part.
It is the process of removing material through abrasive action.
Yeah, very good. Very good. This grinding is the process of removing the material by using the abrasive grains. So basically we have a grinding wheel. In this grinding wheel we have the abrasive grains. These abrasive grains are there. So this abrasive grains, when come in contact with the workpiece, it removes the material. Basically grinding is used for the finishing process. The MRR of grinding is very low, but it is generally used for finishing process. If you want to finish any rough finishing or smooth finishing, this abrasive is used to cut the material and make the surface finish good. Right? This abrasive has the self-sharpening characteristic. Which means that, for example, this is abrasive. It is removing the material from a workpiece. So after this is sharp, na? This is sharp. After some times of cutting, it will become blunt. It is sharp. Now it become blunt. So if it will become blunt, then it will not be able to cut the material now. It will only rub. Then friction will increase. Then they have the characteristics as that the new the new abrasives come into picture. Because of that, now again it can cut new abrasive come. This is the self-sharpening characteristic of the grinding wheel. Okay. So we'll see about the grinding something. Okay. Okay. Grinding is an abrasive machining process that uses the grinding wheel. We have seen cutting tool or sharp edges of abrasive grain. This is not required. Okay. So we can see here the workpiece. You can see here the workpiece. These are the abrasive, and the grinding wheel is rotating and chips are forming. This is the method of grinding with the help of abrasive grains. Now this is very important. Please listen it very carefully. It is very important. In grinding mainly you are asked about the question about the grinding wheel specification. So how to design a grinding wheel. So this is about the specification. First of all, this you need to answer the grain type. है ना कि the abrasive which are used in the wheel, which are having which grain. If the letter A comes, then the grain type will be aluminum oxide. If the letter C comes, then the grain side would be silicon carbide. Because in exam you will get the question of you will be having this ABC, and you have to determine which grain size is there, what type of grinding wheel is used. Okay. See. So grain type will, when you will have A, then you will call aluminum. This you need to learn it. You need to by heart it. If grain type is A, then it is aluminum oxide. If grain type is C, it is called silicon carbide. Now after grain type, you have grain size. This is the order. You have to learn in the order. This is the order. First comes the grain type, then comes the grain size, then comes the grade, then comes the wheel structure, then the bond. This 5 you need to learn. Only 5. Grain type, grain size, grade, wheel structure and bond type. Now you have to learn. So grain type I have explained. A means aluminum oxide, C means silicon carbide. Only this 2. In grain type you need to see if the grain size value is from 10 to 24, it is coarse structure. If it is 30 to 60, it is medium structure. It is 80 to 180, it is fine. And 220, it is very fine. So this also you need to learn. This you need to remember. Okay? Then grade. Grade would be, if grade is from A to G, it is soft grade. From H to P, it is medium grade. From Q to Z, it is hard grade. This you need to remember. Then is the wheel structure. If the wheel structure 1 to 4 dense, 5 to 8 normal, 9 to 6 open. This you need to learn. And third is the bond type. What? Because there are different types of abrasives which has to be bonded to wheel. So you need some bonding agent. So if B, then it is resinod. If E, then shellac. R, then rubber. S, then silicate. V for vitrified. These are type of bond used in the, sorry, 1 second. These are the type of bond used in the grinding wheel. So basically this type of question you will get. See, you will get key, this type of question you are getting. This indicate, what it indicates? First A means it is a aluminum oxide grade. So you have this A46, J5, V8, right? So A means it is the aluminum oxide grade. Second is again, it is 46, right? 46. So 46 means it is coming in this range. This means it is the medium grade, medium grain size. Then its value is J5. So J means it comes in this na, it is medium grade. And 5 means it is a normal structure. And V8, V means it is a having vitrified bond. So this you have to learn. If you want to take a photo of this, please take it. This has nothing to be teased. This has to be remembered. Fine? Hello?
Yes, sir.
This you have to learn. This is very, you have to by heart it. Okay, na? I'm moving to the next slide, na? Okay. So in case of grinding also you have a formula for the undeformed chip thickness, which is given by this one. T is equal to 4V upon VCR under root D by D and whole under square, where big D is the grinding wheel diameter, D is the depth of cut, small v is the work speed, big V is the cutting speed, this R is the some ratio mean chip width to mean chip thickness. It is given by B by T by 2. So this formula you need to remember. This is also very important. Direct questions are asked on the basis of formula. Just remember the formula. Fine. Okay. So grinding force and specific energy, this is not required. This is very extra. In grinding also 3 type of force are there. One is along the feed direction, one is along the cutting direction, and one in radial. So this is there. And specific cutting energy in grinding is also given by what is there? Power upon MMR. Power upon MRR. Where power is what? The cutting force into velocity, and MRR is VBD. Where V is cutting speed, B is the width of cut, and D is the depth of cut. So this you should know. This is not required at all. So this is basic. This is very basics. Okay. Have any doubt? We will move to next question then. We will move to now answer question. Fine.
Yes, sir.
Okay. Before starting the tutorial class, I just want to teach you one thing in 5 minutes. See what happened now. In grinding, we had a term called bond strength. Please listen this very carefully. Bond strength. Okay. So the bond strength of the grinding means how strong abrasives are attached to the wheel. Okay. Okay. So if I'll say this grinding bond strength is very high, what does you mean from this? Ki the abrasives are strong, attached very strongly to the wheel, right? Hello?
Yes, sir.
Okay. So this means if a grinding have a very strong bond strength, that means the abrasives are attached very strongly. But if for example I am grinding a very hard material, right? I am grinding a very hard material, then first the abrasives are very sharp. See, it is very sharp. But after some time, because the material is very hard, it will become blunt. है ना? It will become blunt, right? But now I told you grinding have this self-sharpening characteristic. So it should again come sharp. It should become again sharp. But the bond strength is very high here. So you can see the bond strength is very high. So because of that, it will not allow this blunt abrasive to go and the new abrasive to come, right? Are you getting?
Yes, sir.
Then if it will not allow, then the new sharp tool will not come, because of that this blunt tool will remain. Because of this, what will happen? Now there will be no cutting. There will be no cutting. There will be only rubbing. The wheel will only rub the workpiece. There will be no cutting. So there will be increase in friction. This process is called wheel glazing. This is very important. What is wheel glazing? It is a process where the grinding abrasive tool only rub with the workpiece, there is no cutting. And why this happens? When a grinding wheel with high bond strength cuts a harder material. Therefore, if your grinding wheel is grinding, this is grinding wheel and this is material, it is hard, then you should cut the softer material, and if it is soft, it should cut the higher material. Right? This is the one concept which I was going to tell you. Okay. Have you understood this?
Yes, sir.
Okay. Now we will go to the question answer session. So please bring your copy and pen. We'll start the question answer now. Please bring your copy and a pen. Okay. Can we start it?
Yes, sir.
Okay. So please read the question. A mild seal of, I said, whatever you are seeing, please write 130 diameter. So D is given 130. It is a turning process. Huh? It is a turning process. Turning process. Feed velocity, matlab VF is given 2 mm per second. And rotational speed N is given 50 rpm, revolution per minute. The cutting speed and the feed are given. Cutting speed and the feed. So, what are the cutting speed and the feed? Wait. There is something problem. 1 second. Cutting speed and feed are respectively. 1 second. Okay, I have moved to second question. This is first. We'll do the first question. Okay, we'll do the second question first. So what we have to find? The cutting speed and feed. Right. Feed in mm per revolution. It is asking feed rate. It is asking F and cutting speed. Can you do this, please? Very simple formula. Please do it. Please do it in 2 minutes. Have you done this? Hello? Hello?
Sir,
Yes?
sir, we have to convert the values first, or directly we have to do with the same value.
It is asked na, cutting speed in meter per second. According to this, you need to convert.
Yes, sir.
See, it is very easy. Cutting speed is how much? You know it is pi dn, but it is in meter per minute, na? You need to find it in meter per second. They will do pi dn by 60. You know pi is 3.14, d is 130, but it is mm. It is mm. Then you have to do 130 by 1000. And n is how much? 500. Please solve it. How much you are getting? How much you are getting? Hello?
3.4 meter per second.
Yeah, 3.4 meter per second. This is okay na, easy. You find in meter per second, then you converted 130 by 1000 and n by 60 just to convert in this. Fine? Can I move to? Then one is feed your mm per revolution. So you know that feed velocity is feed into n, right? So feed will be how much? Vf by n. what is your VF? VF is 2, है ना, and this is 500, but this is you want in mm per revolution, and this is mm per second. So you need to convert this by in second na to cut it. So you will do by 60. So you will do into 60. How much you are getting? This you understood? How it came?
Yes, sir.
Understood na? Okay. So what is the answer? 0.24
0.24.
mm per revolution. Everyone got this na?
Yes, sir.
Okay, so we'll move to the second question is over. We'll go to the first question. What is saying? A mild steel bar of 50 mm diameter. So diameter is around 50 mm. Having turned using a tool with signature. This is given a tool signature. ASA standard. ASA standard value are given. Right? In ASA standard, first is rake angle. So alpha side cutting rake angle, then end cutting rake angle, then you have the clearance angle, है ना? You have the clearance angle, the delta, side cutting clearance angle, side cutting end cutting, then side cutting. Then you have the end cutting edge angle, side cutting edge angle, then radius in inch. Okay, so here you have end cutting edge angle and side cutting edge angle. So gamma E is given 10 and gamma S is given 15, right? And the feed rate and depth of cut are given. So feed rate F is given 0.3 mm per revolution and D is given 0.5 mm. So first you need to find the undeformed chip stiffness. So undeformed chip stiffness ka formula what is there? Can anyone tell me? Hello?
D by cos beta.
Huh? It is F cos gamma S.
Oh, हाँ ठीक से.
And B is D by cos gamma S.
Yes, sir.
So F you know 0.3 into cos gamma S is 15. It is D is how much? 0.5 upon cos 15. Simple, very simple. Just you need to find the gamma S. So gamma S you get from here. This 15 gamma S is given. You need to remember this. You need to remember this. Just solve it. Tell me the answer.
The chip thickness is 0.2897.
Chip thickness is how much?
0.2897.
0.2897. Okay. This is how much microns? Mm. And width of cut is?
0.5176.
Right. Fine. So can I move to next question? This is okay na? This is done na?
Yes, sir.
Okay. So I am moving to third question. See. Now please read the question. The deviation of the machine surface is 5 points from the mean line over a surface R for our surface length of 4 mm are itta. So for example, it is said you have a surface length of 4 mm. Here you have 5 points. 5 point can be anything. 1 point can be here, 1 can be here, 1 can be here, 1 can be here, it can be here. So these values are given. One value is given to be 4, one values are given to be 7, one is given to be 9, one is given to be 5, and one is given to be 4 knots. 7, 9, 5, 8 and 11. Fine? It is given like this. Hello?
Yes, sir.
See, I'll draw it again. You have a length. Length is of 4 mm. In this you have 5 points. One can be here, right? One can be here, one can be here, one can be here, one can be anywhere. So one is say 5, one is say 7, one is say 8, one is say 9, one is say 11. All are in microns. So it is find the root mean h square surface roughness. So h of root mean square. What is the formula? Can anyone tell me? Can anyone tell me the formula? Hello?
Under root 5 square plus 7 square up to 11
Right.
square.
Under root 5 square plus 7 square plus 11 square plus 9 square plus 8 square by 5. What is the answer? Please calculate the answer.
Sir, 8.2462.
8
2462.
right. Its answer is around 8.246 है ना micron. If it would have asked find the simple center line average, then what you have done? 5 plus 7 plus 11 plus 9 plus 8 by 5. Okay, don't take 9 to be negative because it is downside. It can be, take every value to be positive. Okay, in case of center line, but in case of root mean square,
Yes,
take
sir.
the square, divide and then square root. Fine na? Can we move to next question? Hello? Hello?
Yes, sir.
Yes, sir.
Okay na? Can we move to next question? Okay.
Okay, sir.
Yes, sir.
See, during the turning of a mild steel of its diameter is given 120 mm. Okay, two different tools are used. So one is tool 1 and another is tool 2. Two different tools are used. Okay, in one tool nose radius is very small. So here R is very small, so we can, it is very small. It is almost equal to 0. Very small means. And the side cutting and the end cutting edge angles are given. Matlab gamma S is given 20 and gamma E is given 10. In the other tool, the nose radius, some nose radius value is given 0.6 mm. And the feed in both cases are here also feed is value is 0.4 mm per revolution. Here also 0.44 mm per revolution. Up to the peak to valley height h, you need to find h in here and find h here. Please find it in both cases. Please find it and tell me the answer. When what formula we need to use, please see. Hello, please solve it. Hello. Have you got the answer? Hello. Hello. Have you got the answer?
0.066, sir.
How much?
0.066.
For which one?
Tool 1.
To which tool one? What formula you will use?
F by tan CS plus cot.
Yeah, tan gamma s plus cot gamma e. So the answer will come to 0.0663, right? And here what formula will use? F square by 8r.
8R.
What is the form? What is the answer? 0.033. Fine. Can we move to next question? Hello.
Yes, sir.
Can we move to next question?
Yes, sir.
Okay.
Yes,
fine.
sir.
Fine. See, this is very important. This is very good question. Very important question. See, in a turning operation, the average cutting zone temperature is obtained as this much. It is given that average cutting temperature is directly proportional to Vc power 0.6, F power 0.55 and T power 0.4. ठीक है? It is given directly. To remove this proportionality sign, we can introduce a constant, right? You know this? Then theta average can be written as k times of this can be any constant, Vc power 0.6, F power 0.55 and T power 0.4, right? This now it is saying कि by how much percentage the average cutting zone temperature will increase if the cutting velocity Vc is halved. Now what will happen? This is theta average 1. Now Vc2 will become Vc by 2 half. Feed 2 will become twice of F and depth of cut T will become twice of T, right? If I'll make Vc to half and feed and depth of cut to twice, then what will be the average percentage change in the temperature? Can you do it, or you want me to do it? Hello? 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 My voice is audible. Hello? Hello?
Yes, sir.
Okay. So in this, what you want if you are reducing the speed by half, feed by double, and this depth of cut by double, what is the change in the cutting temperature? So this I am doing. See, this theta 1 value is this much. So the theta average 2 value will become, it will become k. Vc is how much now? Vc2 is Vc by 2. It will become 2.6. Feed will become twice of feed, 0.55, and T will become twice, 2T, 0.4. This is 1, this is 2. So the percentage change will be what? Theta 2 minus theta 1 upon theta 1. So theta 2 is how much? I am taking theta 2 is this, key V by 2, 0.6 minus 2F, 0.55 into 2T, 0.4 minus theta 1 is K, V power 0.6 into F, 0.55, T, 0.4 upon theta 1, which is K, V power 0.6, F power 0.55 and T power 0.4. Please solve it. You just need to solve it. See, K gone, K gone, K gone. V, F, T all gone. You just need to simplify it. Please tell me the answer. Hello? Have you understood how it is done? And if you need to find the percentage, multiply by 100. Hello? Have you understood how it is solved? Hello, can you hear me? Hello?
Yes, sir.
Okay.
Yes, sir.
Have you solved it? I'm telling you the answer. If you solve it, the answer will come to 27.456%. Please solve it. I am going to the next question. Okay. See, in a plain milling operation, the cutter diameter is 110. So cutter diameter means D is 110. Number of teeth means N is 12. Cutter speed V or N, big N, is 50 rpm. Table speed means V is 130 mm per meter. Depth of cut T is 2 mm. The ideal peak to valley roughness H. This is very simple. For milling, H is how much? V square, it's VF actually. VF square upon pi d n square. So we know for milling the value of peak to valley roughness value is Vf square, which is the feed velocity square upon pi d n square, where where d is the cutter dia, n is the number of edges, and n is the spindle rpm. Just can anyone solve this? Hello?
Sir.
Please solve it. Just put the formula and solve it. Vf is 130 square upon pi, d is 110, n is 12 square, and n is 50 square.
Sir, 1.3584.
Hello?
Hello.
Yes.
So 1.3584 into 10 raised to minus 4.
One second. Actually, by mistake I have written the formula wrong. It is not pi, it is 4 actually. So please correct it. I was just checking it. It is not pi, it is 4. Now solve it, please. Vf square upon 4 dn square n square.
So the answer is 1.066 into 10 raised to minus 4.
066
into 10 raised to minus 4.
Okay, fine.
Yes, sir.
Okay, fine. We'll move to the next question. Okay. Everyone is done, na? Hello?
Yes, sir.
Okay.
Yes, sir.
Now, please tell this. Which of the following statement are correct? Please read it. In down milling, the chip thickness is maximum at the start of the cut and zero at the end of the cut. In down milling, the chip thickness is zero at start and maximum at end. In up milling, chip thickness is maximum at start and zero at end. And in up milling, chip thickness is zero at start and maximum at end. Please tell it. I have just taught you this. Can you tell me the answer? Hello? Can you tell me the answer? Hello?
In upwelling, chip thickness is 0 at the start
Okay.
and maximum at the end cut.
Okay, right. And for down?
Downwelling, at start it will be maximum and at end it will be minimum.
Okay, right. So I have taught already कि in up milling, you know, when the cutter and the feed direction is opposite. If cutter is moving velocity here, then the feed direction is opposite, right? So the chip thickness start from 0 and it gradually increase to maximum value. But in case of down milling, we have the cutter direction and the feed direction to be same. If cutter is moving like this here, then the feed direction is also same. So it starts from the maximum and then it goes to the minimum. So the answer is A and D. Okay. Fine, na? Can I move to next question?
Yes, sir.
Okay. See, in drilling operation, the twist drill diameter, just see, the dia is given to be 30 mm, feed is given to be 0.54 mm per revolution. The point angle is given to be, point angle means beta is given to be 120 degree and helix angle psi is given to be 30 degree. The normal rake angle at the middle of the cutting edge and the cutting chip thickness. Can you solve it, please? Can you solve it? What is the formula for the rake angle? Can anyone tell me?
Sir,
Huh? Hello? Can anyone tell me the formula for the cutting rake angle, normal rake angle? Hello? Hello?
Sir,
Yes, please tell me.
sir, RA tan psi upon d by 2 sin beta by 2.
RA tan psi upon
D by 2 sin beta by 2.
Okay. In question it has asked at the middle of the cutting edge. So I told you na, at the middle of the cutting edge, RA is equal to D by 4. I explained you, right? So when you put this RA equal to D by 4 here, then what it will become? It will become na tan psi upon 2 sin beta by 2. Just put RA is equal to D by 4 here. Okay, and
Yes.
this is tan alpha n. Now put the answer. Tan psi. Psi is how much? 30 degrees. 2 into sin beta by 2. Beta is how much? 120. 120 by 2 is 60 degrees. So tan 30 upon 2 tan 60 degree. Take the tan inverse. What is the value of alpha n? Please tell me. See, this I have explained. It is asked in the middle of the cutting edge. So therefore RA is equal to D by 4. if it would have asked कि at the middle of the drill axis, then RA would be D by 2.
Sir, 18.43.
Right. Answer is 18.44. Second question is uncut chip thickness. What is the value of uncut chip thickness for drilling? Do you know the formula? Hello? What is the formula for uncut chip thickness for drilling? It's F by 2 sine beta by 2. Right? What is F? F value you know, 0.4 by 2 into sine 60 degree. What is the answer? Hello? Hello?
Sir, 0.1732.
0.1732. Right. This is very simple. So everyone has done this. Can you move to next part?
Yes, sir.
Okay. See, now it is the grinding question where you have given what you have given. The wheel size is, this is actually dia. It is dia. It is 5. So wheel size is 350 into 35. This means the diameter is 350 mm. Okay. Number of cutting point per mm square, which is C. C is given to be 8. Wheel RPM N is given to be 3000 revolution per minute. Okay. Work speed is how much V? It is given to be 150 mm per minute. Depth of cut, which is T, is equal to 0.1 mm, and the value of the ratio of mean, which is R. So R is given to be 16. You need to find the undeformed chip thickness. So do you know the formula of undeformed chip thickness in case of grinding? Everything is given. You know na, this is given by 4 small v upon VCR under root d by d का whole square root. Hello?
Yes, sir.
You can put the formula. Small v is given 150, right? Big V you need to find. C is given how much? 8. R is given 16. Small d is given this depth of cut. This is small d 0.1, and this big D is also given 350 की power half. How to calculate V? V is pi dn by 60. V is pi dn by 60, or you don't need to find pi dn by 60 because this is also in minute na. This is also in minute. 150 is in minute, so you don't need to find pi, you don't need to do pi dn by 60. If this was in second, then you need to convert this into second, but here it is in minute, so you can leave it in minute only. So just find pi. D is how much? 350. N is how much? N is 3000. So you get V. How much V you are getting? How much V you are getting? Hello?
329730.
D 32.
D is 329700.
1 second. 329700. Okay, fine. What? How much you are T? How much you are getting? T, how much you are getting? Just put the value of V.
So 1.549 into 10 raised to minus 4.
Right. 1.5 something 10 to the power minus 4. Right. This is a very simple question. You just need to fit the formulas and put the values. One thing you need to take care is that the unit of this small v, which is the work speed and the cutting speed, both have the same unit. If it's given in meter per minute, you don't have to do by 60. If it is given in meter per second, then you need to convert the cutting speed into meter per second and pi dn by 60. Fine. This only you need to take care. Rest is only the formula. Just put the values and get the answer. Okay, can we go to next question? Hello?
Yes, sir.
Yes, sir.
Okay. See, a grinding wheel which have this specification, you need to tell now based on the characteristic which we have studied. Can you look at this number and tell what is the specification of the grinding wheel? See, you can directly eliminate. First of all, you can see it is R. R is for what? R is for rubber bond. 2 are the resinoid bond. See, B is resinoid. Sorry, B is resinoid and D is resinoid. So this B and C are wrong. Directly you can do it. Because R stands for rubber bond, right? So either it should be A or C. Now you check. You can see A is for aluminum oxide.
Sir, C.
Right. Okay. C is right. C is the answer. Why? See, we can see A is aluminum oxide. 50 is the grain size. So 50 comes under medium grain size. And here it is written fine. So A is also wrong. The answer is C. Medium grain size. Okay. And M means the medium grade. R is the rubber bond. So answer is C. Fine. You just need to remember that chart. That chart we had discussed. Na, this one. This chart you need to remember. This first comes. We have seen the first comes grain size, then grain first grain type, then grain size, then grade, then wheel structure, and then bond type. If grain type, generally grain type, 2 types of grain types are there, A and C. A means aluminum oxide, C means silicon carbide, and grain size you need to remember. Keep from 10 to 24 coarse, then 30 to 60 medium. It was 50, then it was medium. 80 to 180 fine, then higher than that very fine. Grade you have to see. It was M, then M comes between this, then it is medium. Wheel structure it was 5, 5 is the normal, it's normal. Like that you need to remember. Okay. So it's okay na? Hello? Hello?
Yes,
sir.
Yes.
Okay then, so do you have any doubt?
No, sir.
No, sir.
Okay then.
Sir,
Okay,
in
yeah,
exam,
please.
how many questions will come?
What?
In the exam,
Uh-huh.
how many questions will be there?
Yeah,
And
exactly number of
what-
question that I don't know because that will be decided by the professor. But it
Okay,
will be mostly the MCQs only. Multiple choice question will only come, and mostly the numericals and this some theories what we are discussing.
Okay.
Okay then please do the assignment on time, and then if you have any doubt regarding the assignment 6, we will discuss on the next class, and I'll upload this video on the YouTube. Please, if you have any doubt, please check from there. Okay,
Okay.
thank you.
Thank you,
Thank
sir.
you, sir.